Alright, so now we're going to start looking at doing data visualization and plotting with ggplot2. So just so you know, in R there's a couple different environments for doing plot generation and graphing and whatnot. So for example, there are base graphics in R, like through the plot function, and there's also the lattice package. But I'm a real big fan of ggplot, and also is pretty well integrated into the tidyverse and whatnot. I find it's really intuitive and it's really powerful once you kind of figure out the philosophy that it's like based around. So this is two parts. The first part we're going to look at just the basics of making graphs and assigning aesthetic mappings, and then in the second part I'll just show you some examples of cleaning up and making graphs look pretty by doing things like altering the axes and the colors and the labels and whatnot. So first off, you should just for now, I just want you to focus on trying to understand the basic syntax and the aesthetic mappings. Again, ggplot just is part of the tidyverse, so if you want to use the cheat sheet, you can just go here to help, cheat sheets, and then open up the ggplot cheat sheet here. So this is a really good reference. It's also really well documented online, so there's lots of good options for getting help. So anyway, there's the cheat sheet. We'll leave that up because we may go back to that later. Okay, so the basic idea behind ggplot is based around this concept called the grammar of graphics, which was put together by this guy named Leland Wilkinson. And it's almost like diagramming a sentence if you've had to do that like in an English class. So the idea is that you can kind of break down a graph into different like components to kind of understand like how it functions. And ggplot was basically written with that kind of idea in mind, where we can take these components of a graph and describe them as settings and geometries and whatnot within code. So that's effectively the idea. Okay, so I'm going to read in some data. This is this High Plains data set. I made this. It's just basically some physical, like environmental data summarized on counties for the High Plain states in the U.S. So basically, we're reading this in from a directory here as a CSV file. So we run that there. See here we get this object, and you can see it has a bunch of different fields in there. We're mainly going to play with the percent forest, the elevation, the temperature, and the precipitation. So these are all data that were summarized from geospatial data at the county level. Okay, so let's look at how you generate a basic graph with ggplot. So first off, you need to call in the ggplot library, which I don't think I did. So let me go back up and do that. Maybe I didn't. Let me see here. Maybe that. Oh, never mind. It was in the first block here. So it's a library you've called in. So library ggplot2. Once it's in, you can obviously start using it. So here's a basic graph. This is just a basic histogram where I'm showing the distribution of percent forest cover at the county level. So plots are initiated with the ggplot function. The first argument in the function is the data set you're using, so the data frame. And then inside of this other function, stands for aesthetics, or aesthetic mappings. So this is how you're going to display variables within the graph space. So effectively what I'm doing here is I'm assigning the percent forest variable to the position on the x-axis. And since this is a histogram, that's actually the only geometry that's required. So then the next component and any other subsequent components of a graph, they're all strung together with the plus sign here. This might seem a little confusing because you might think, well, they could use like the forward pipe function, like what was commonly used in the tidyverse, but you're really not stringing together separate functions here. You're just kind of adding components to the graph. So they're strung together here with the plus sign. And then there's all these different geoms that define different types of geometries and different types of graphs. So this is Geohistogram, which is used to make a histogram. And the argument here is bin width, which is the width of each bin. So I set this to 5, so it's basically each bin will aggregate over 5% of percent forest cover. Okay, so we run that. We get that here. So this is a very simple histogram, and it just gives you a little bit of an idea of the distribution of the data. So you can see that most of the counties in this region actually have a fairly low percent forest cover, but there are some that go out higher, obviously, because there's a bit of a right tail, and there's none that's higher than like 50%. This isn't a heavily forested part of the country. So just a few notes. This is like the base look of a ggplot graph that has this like gray background. There's generally a gap between the margins and the plot space that doesn't butt up against it. But there's ways to change all of that, and we're going to look at that mainly in the second component here. So let's just look at a few other examples. This is the same thing, but I'm just changing the bin width to 2. So now it's only aggregating over 2% as opposed to 5%. Again, you could just continue to play around with this and see how it impacts the look of the graph. So anyway, that's an example of a very simple univariate graph where you're only showing one variable. So we map the percent forest to the x-axis, and then the y-axis, because this is a histogram, is showing the count, or the number of records, in this case counties, that fall into that category. So it's a very simple. So that's a very simple graph with Geomhistogram. Okay, this is just another one, again showing a different bin width, and also for different data. So this is for the temperature data. I believe this is in Celsius. So you can see the distribution there of the temperature data aggregated over the county. So that's like the mean across the county of the average annual temperature. But again, same thing. All we really did here was we just changed the x variable to a different variable, and we changed the bin width, but all the other components are the same. So it's pretty consistent in terms of generating different graphs. Okay, so here's another example of a univariate graph. This is a kernel density plot, where effectively you're fitting a kernel density function through the curve to look at the data. And to look at the distribution of the data. And this is actually fairly similar to a histogram in that it's used to look at the, again, distribution of a single variable or univariate graph. So it's basically the same thing here. The only real difference is we've changed out the geometry from Geom Histogram to Geom Density. And I've also added in the second argument here, which is density, which defines what the y-axis will be. And we'll look at a few other options here in a minute. And then I'm also setting a fill collar. One thing you might note here is that fill is another like graphical parameter, like a collar of, or the fill collar of an object, in this case of the kernel density plot. And here we're just mapping it to a collar as opposed to a variable. So you can map to variables, and you can also map to like constants like collars or widths or point symbols or whatever. We'll see some examples of that as we move on. So anyway, here's an example of that. That's a kernel density plot. It's basically the same thing as this, but just using a different geometry. So instead of a histogram, we're getting this kernel density function. Again, you can change this. So if instead of getting density, you could just get the count. So that's just ... count ... and then it just is going to change the y-axis there to count as opposed to density. There you go. Yeah, so that's that. Let's look at another example here. So this is just adding in some additional settings. So again, high plains data, we're looking at the temperature. The y-axis will be count as opposed to density. Same geometry, so this is Geom Density. And we're going to fill it with red. The color in this case is the outline color, and we're setting that to gray, and then we're setting the size to 3, which is the size of the outline. So you can see that there. So if I made this like something crazy, I'm just going to put 20, which is kind of ridiculous, but it makes this like really wide outline, right? So that, you have control over the look and feel of the graph, right? Yeah, you could also, well, we'll look at that in a minute, but anyway, so that's just a couple extra settings. Here's one where there is no fill, so we're setting the fill color to NA as opposed to a collar. So now we get the line, but not the fill. Oh, one thing that's worth mentioning, actually, I don't know if I do this lower down. I'm just going to do this real quick. You can't have multiple geometries, so we could do like actually, let's just do, let's do this. So we'll do plus, and then Geom histogram. And now it's going to plot a histogram alongside of the kernel density plot. So now we have two geometries in the same space. Now, one thing to note here is that obviously these two graphs, they have the same x and y axis, so thus you can plot them in the same space. If they have different x and y axes, then obviously they're not going to be able to be plotted in the same space. Okay, this is just showing another adjustment here, so you can change the density or the level of detail in the kernel density plot by setting this adjust argument. Lower values are going to show more local variability, as you can see here, whereas larger values are going to kind of smooth out the curve a bit. That's probably too much. One thing with histograms and kernel density plots is there's not necessarily a right answer for how generalized or how detailed you want these curves to be. You generally just kind of play with it. So like this is probably too generalized. Maybe this is a little bit too detailed, but again, there's not really a right answer there. Okay, so now let's look at a different type of plot. So now we're going to look at a box plot, and box plots are designed to show the distribution of a single variable. And generally you have a couple different features that are shown. We'll just make a box plot and then we'll talk about it. Okay, so here's a basic box plot for elevation. So again, this is the basic ggplot syntax. So we initiate the plot with the ggplot function. This is the data. We're mapping the elevation to the y-axis, and then we're plotting it as a box plot. And a box plot only requires a y; it doesn't require an x variable. So this is a very basic box plot. So we have so this is the distribution. So the box is the interquartile range. The line in the middle there is the median. And then we have the range here from minimum up to max. Now you might be wondering why there are points drawn. So in R and with ggplot specifically, the default is that if a high value is more than 1.5 IQR from the third quartile, then they're mapped as points. And if low values are lower than 1.5 IQR from the first quartile, then they're mapped as points. So there's some high values here that are considered kind of more extreme, I guess. Okay, just for real quick, I wonder if it'll let me do this. I'm going to change this to X and see what happens. There we go. Yeah, so now you can see it just flipped it over. So now we're mapping the elevation to the x-axis as opposed to the y-axis. And the y-axis in this case really doesn't mean anything. It's because it's just one category. So switch this back to y. Okay, cool. So that's that. So basically, this first set of graphs we looked at a single variable. So where we have histogram or kernel density plot or a box plot. Okay, so now we're going to look at some examples where we're comparing categories. So the idea here is that we want to look at the distribution of a continuous variable relative to a category. Okay, so what I'm doing here is I'm subsetting out just three states from the High Plains data set. So just the counties that are in North Dakota, Utah, and Kansas. And then that data is going to get pumped into is going to be funneled into ggplot here. We're mapping x to the temperature to the x-axis. The y-axis is going to be density. Again, that could be count. And then now we're actually going to use the fill color to map to differentiate the states. So let's run this and see what it looks like. Okay, so this is what we get. So this is our density plot. So because we mapped fill to state, we're getting actually a different plot for each of the three categories to compare them, as opposed to getting one. So for example, if I remove this fill, it's just going to plot them all together and not differentiate them by category. So that's just one plot for all of them. Now, let me just do an undo here, and then when we get this back, now we're differentiating them by the fill color. You might be wondering, why is this fill as opposed to color? Well, it turns out that for the kernel density plot, the color is actually the outline. So if we set the color there, we'll just get different outlines for each plot. One thing that's kind of confusing is not always consistent between whether color means a fill or an outline. It just kind of depends on the geometry. So you'll get used to that as you play around with these. And luckily, it's really well documented. So, yeah. So let me show you another thing while we're talking about this. So what I did here is kind of in 2 steps, right? So I used dplyr here to filter, to subset out just the counties in these 3 states. And then I took that result and I put that into ggplot in order to make the graph. Now I could run this all together with the forward pipe. So we could do something like this. So, and we don't need to save this to a variable now. So we're just going to get rid of that. So we're going to take the high plains data, we're going to filter it, and then we take the filtered result and we pump that into the ggplot. Now this is going to fail. Let me show you that. So it says error in ggplot. Yeah. So basically, because we are we're pumping the data in, we can't include or don't need to include this first argument, the data argument in ggplot. So we can get rid of that, and now this should work for us. There we go. So same thing. So anyway, you can include these plots as part of a piping through the piping operations if you want, or obviously you don't have to. Another side note is this alpha. What that specifies is the transparency. So if we didn't set an alpha here, let me just run this real quick. Then you can see that there's no transparency. But when we add an alpha, then that makes it a little easier to see through, and you can kind of actually see the different curves. So anyway, with this data, you can see there are some clear differences between the distribution of temperatures for these 3 states, right? So we have lower temperatures for North Dakota, higher temperatures for Kansas, and then a lot of variability for Utah. So yeah. And then another just quick note, again, if we wanted, we could to map something else, all we'd have to do is go in here and swap this out. So if we want to do like elevation, now we have basically the same graph, but for elevation as opposed to temperature. So look at our % forest. So anyway, that's one thing. Again, it's really consistent, so it's pretty easy to set up and use. Okay, cool. Let's see what we're doing here. This is basically the same thing except for precip. So again, we're taking our data that we subset out to 3 states, and now we're plotting the precip as opposed to the temperature. So it's just changing out the variable map to x. That's all we were really doing. Okay, again, this is a box plot, but now we're basically going to create a group box plot where we're differentiating we're going to get a different box plot for each state. So if we run this, now instead of getting one box plot, we're getting, again, a separate box plot for each state. Now, if I remove the X mapping here, then we would just get back our elevations for like together as opposed to broken up by state. So with the X aesthetic there. Okay, so anyway, that's an example of getting a group box plot, and you can see the clear differences in elevation here, like for example, Colorado, Utah, Wyoming have a lot of mountainous areas versus, like Kansas versus North Dakota and South Dakota. Okay, now it is also possible to map the same variable to more than one aesthetic, and that's what I'm doing here. So here I'm mapping the state to the x-axis, and then I'm also mapping it to the fill color. So again, if we run this, now I'll get a different color for each of the states, and also the states will be at a different position along the x-axis. Now, really, this isn't necessary, but it might make a little bit better visualization. And or what I mean is, you don't really need the collars to differentiate the states because they're just differentiated by their position on the x-axis. Again, if we did something like collar here, then this would be the outline collar as opposed to the fill collar. Now, just so you're probably wondering, well, how do I pick my own collars? How would I edit the labels? Again, don't worry about that for now. We're going to look at that when we get into the graph editing in the next section. For now, all I'm really wanting you to do is just understand how we build these basic graphs and use these aesthetic mappings and whatnot. All right, cool. So this is just another example. It's just with precip. So again, we have our states mapped to the fill collar, and there we go. And then we get our different graphs for each one, and differentiated by their fill collar and their position on the x-axis. And let's see here, what am I doing in this example, which is different? Oh, I already showed you this. Again, in this case, collar is the outline as opposed to the fill. Okay, so one thing again to note here is that you may want to plot things in a different order. So what I'm doing here is I'm using this factor reorder function from 4cats. Here I just read in 4cats. And now I'm reordering it by their median elevation. And then that gets pumped into the aesthetic as opposed to the original data. And what that means now is then we plot it, we get them in a descending order from highest to median elevation to lowest median elevation. So that's what this is doing. So this factor reorder is from 4cats, and we're basically saying we want to reorder the state names based on elevation, and we're going to order them based on the median elevation, and we're going to do that in descending order. There you go. All right, cool. All right, another alternative to a box plot is what's known as a violin plot. So violin plot is basically a kernel density plot that's been flipped over on its side and mirrored. So it kind of looks like the body of a violin. That's why it's called that. So the aesthetics here are basically the same. So we have the state name mapped to the fill and the x-axis position, and then we're showing y. But now we just swap the geometry out for violin as opposed to box plot. So if we run that, we get this. So again, these are like kernel density plots. They've just been turned on their side and mirrored. So you can kind of see the distribution there. Again, it's not really necessary for the fill. We're just kind of doing that to make it a little bit more visually appealing. But again, if we remove this, we would just get their position on the x-axis. Also, I think we could do like the collar if we wanted, right? And just change the outline collar as opposed to the fill collar. All right. Now, again, if you have geometries that have the same x and y axis, so for example, like the histograms and the kernel density plots, you can graph them in the same space. And for the case of a violin plot and a box plot, they can have the same axes. So like the categories on the x-axis and then the value that you're comparing on the y-axis. So here I'm just adding two geometries. So we have the violin in the back and then the box plot above it. Note that the order depends on the order at which the geometries draw will depend on the order that you specify them. So for example, if I swap these around and get rid of this and I had to add the plus sign back on there, then now the violin plot is above the box plot, right? This isn't super effective because they just don't overlap well, right? Get this back to where it was. There we go. So we're going to play with this and try to make it a little bit better. So what I'm doing here is I'm in the box plot, the Geom box plot, I'm changing the width so it's not as wide, and I'm changing the fill color to gray. And this creates this type of result, right? Which I think is a little bit more visually appealing. So you might be wondering, well, but the fill is defined here, so how does it know which fill to use? So there's kind of like a precedence order here. So if you specify an argument within the geom, it's going to supersede the argument that was provided in the ggplot function. So since we had violin plot had no internal arguments, it's accepting the x, y, and fill positions from the ggplot. And for Geom box plot, it's accepting the x and y, but the fill is getting superseded with gray here. You might also be wondering why isn't width and fill in here wrapped inside of one of these aesthetic arguments. Well, that's because they're not being mapped. You're not mapping a variable. You're just mapping a constant. Now, if you did want to map a variable to this, then you'd have to wrap it in the aesthetic function. So that's that. Okay, let's see, what are we doing here? So this I kind of did the opposite. So here I'm making the violin plot gray, but maintain the color, the fill color for the box plot there. And again, we just have the fill now in that argument as opposed to in the box plot argument. Okay. All right. So here I'm just subsetting out the North Dakota, Utah, and Kansas records, and then we're just plotting the temperatures for the 3 of them here in the box plot. And again, we have a violin plot with the color, and then the gray box plot within it. Again, if you wanted, you could do this all in one go. So you could just do your data, pipe that into your filter, and then pipe the results of the filter into your ggplot, and then you'd have to remove the data argument, and then that's all basically just one long pipe now. Oop, did something wrong. Oh, I accidentally removed the H. Put the H back on. There we go. There we go. So that would give you the same result. Okay, these are just some other examples of graphs where you're mainly looking at one variable or trying to differentiate a variable or compare a variable, continuous variable between categories. So here we're using the Geom point, which draws a point based on an XY coordinate. So let's produce that and have a look at it. Okay, so what we have here is we're showing the elevation for 6 random counties. So I just pulled out 6 random counties, and then I put those in the ggplot, and I plotted them out using points. So here the name specifies the position on the x-axis, which is a nominal variable, and then y is specified by the elevation, which is a continuous variable, and then the size argument specifies the size of the dot. So if we wanted, we can make this, way bigger. Let's do like 10. That'll make a much bigger dot. It's kind of ridiculous, but so let's put that back at 2. You can also change the shape. So there are shape arguments, and I always forget these. So let me just have a look real quick. I'm just gonna do point shapes ggplot. We should be able to find an example here. Here we go. So these are the different point shapes. Note some of these have a fill, some of them don't. Some of them are just an outline. So let's pick one. Let's use the diamond. So that's 23. Move those over here. So if we do shape is equal to 23, that's going to make this a diamond. And note that for diamonds, the color, well, actually we didn't set any arguments, but we can do that. So let's set, we'll do color is equal to, let's see here. We'll set that equal to the name 1. And this should give us an error. Let's see if it does. So it says name 1 not found. And that's because since we're mapping this to an aesthetic, we're going to have to put that inside of the aesthetic argument. And, okay, that should work. Let me get rid of this. There we go. So now we have the color mapped to the different county. But that was actually the outline color. If we wanted to be the fill color, then we could do fill. And then we could do something like change the color to a constant, like let's make it black. And I believe the width is the width size. Let's see. This should be ridiculously big, probably. Oh, maybe that's not what that does. Might be a line width. Actually, not sure. Anyway, there's a different mapping for that, for the outline width that you could change. But I have to look it up. I don't know what it is off the top of my head. Okay. This is a bar plot. So we're showing the for these 6 counties, we're gonna show the elevation as a bar plot. One thing that's kind of weird here is you have to do a stat, and this stat is identity, which basically means you're just returning the value to the axis as opposed to like the mean or something. Okay, so those are some univariate graphs. So now let's look at some multivariate ones. So multivariate graphs are generally used to compare between variables and kind of group when you're doing categories by group like we were doing before with the box plots. That's kind of like a multivariate graph. But here we're looking at multivariate graphs where we have two continuous variables. Okay, so the first thing we're going to look at are scatter plots that allow you to look at the correlation or relationship between two continuous variables. So here we're showing the relationship between the elevation and the temperature. And Geom point draws points, scatter plots are points, so basically we're making a scatter plot. Okay, so this is that graph. So the x-axis is elevation, and the y-axis is temperature, and you can kind of see that there is a bit of a correlation there, right? So higher elevations tend to be associated with lower temperatures. In this case, I think it made sense to map the elevation to the x-axis and the temperature to the y-axis because you can say that elevation impacts temperature as opposed to the other way around. So it's like a dependent-independent variable decision. With Geom point, you do have other things that you can use or map to. So here, again, I'm just using the elevation and temperature, but then I'm actually specifying some other settings. So I have a shape, a color, a fill color, and a size. So again, we basically just change the point size, the point color, and then the outline color. Yep, and its symbol, the diamond as opposed to a circle. All right, another thing you can do when you're using like a scatter plot is you can graph a best fit line, and that's generally done with this Geom smooth. And then you can set a method. Here I'm using method LM, which is for like fitting a line. There's also a method loss for doing like a moving average. So if we run this, we can see here that this spits out a fit line. This gray bar around it has to do with like a confidence interval. One thing you can note here is this doesn't really look like a linear relationship, right? So fitting a line or showing a line might not be super useful. So instead, we can maybe use something else like the loss function. So let's see what that looks like. So basically, this is like a moving average. So that fits a little bit better. It's a moving average. Okay, and then this one is, let's see what we're doing here. This was, yeah, so we're showing the elevation and the temperature, and we're adding, we're just changing the fit line here, and we're adding a line type and a line width. So this line type argument is used to change the type of line, like a solid line versus a dashed line or whatever. And this is the width of the line. So if we run that, you can see here we've got a different line pattern. Another thing you can do when you specify this is you can set this SE, which is the standard error, to false. If you do that, then it doesn't show that confidence interval. It just shows the line. So that's an example where you have a scatter plot with Geom point, and then you're adding some type of fit line to it, either a linear trend or a loss, which is what I'm doing here, which I already did above. Okay, here we're going to map some additional variables to some of these for graphical parameters. So here I'm setting the x to elevation, the y to temperature, as we did before, and I'm setting the size of the point relative to the percent forest cover, and then the color of the point will be relative to a categorical variable or the state that it's in. So if we run that, again, we can see kind of groupings amongst the states, and we maybe see a bit of a pattern where seems like higher elevations tend to have higher percent forest cover. I would argue it's really not that effective. There's probably too much going on there. Again, I'm just trying to show you how you can do some of these different type of mappings. Okay, so, all right, a couple other just kind of side notes here. There are other aesthetics. So this example is where you can add in text. So Geom text allows you to assign a variable to a label. And since there's so many counties, here I'm just subsetting out 10 counties. And then, again, I'm just pumping those into a scatter plot, and then I'm labeling the points. So here you can see that the label has been set relative to the name of the county. And note you can like move labels and stuff. We're not going to get into the details of that. I'm just trying to show you the aesthetics here. So that's what Geom text is for. You can add text to the graph. These are some examples of some line graphs. So this is common for things like a time series or something. The first example here is this maple leaf data set, and this is what's known as a spectral reflectance curve for a maple leaf. So let's plot it and have a look at it. So again, we pull in the data. We map for X, we're mapping the wavelength, and Y, we're mapping the spectral reflectance. And then now instead of geom point, we're using geom line. And it looks something like this. So if you've had something like a remote sensing class, you may be familiar with the spectral reflectance curve, but basically this represents the different wavelengths, and then Y represents the percent reflectance. So this is like blue, that's green, that's red, this is near infrared, and then this is out in the shortwave infrared range. So basically this is what the spectral reflectance curve for a leaf looks like. This is another example of a line graph. This is for another spectral reflectance curve for some features in this from the Avarice data set. And here we're just basically plotting one of those curves. So that's a measure of, I think that's radiance. But basically again it's just a curve. And here I'm actually adding in multiple curves. So one thing that's interesting is, the shape of your data makes a difference in how you would read it in. So if we look at this, we have basically 4 locations. And instead of having a column where it differentiates the locations, each location has its own column, right? So and the header tells you what column it is. So instead of setting like color equal to like the site, instead I basically just add all those data points separately. So in each of these aesthetics, I'm using a different variable. So the first one's A, then B, then C, and then D. But the X is the same for each one, so they're mapped in the same space. And I'm also adding a collar. Note here that the collar could be specified outside of the aesthetic since you're not mapping a variable to it. Here you go. So you might be wondering, why did that map out? That's because I put that in the aesthetics and it thinks it needs a legend for it. So if I just cut this real quick and paste, do the same thing here. And then lastly, I guess I had to do top one too. I forgot to copy that. I guess we'll just, what was that? I guess it was yellow. And then we'll do the same thing here. So we'll cut this out, and we'll move it down here, actually. And we got rid of these commas. So basically, I just took all the color arguments outside the aesthetic mappings, and then I need a comma there. That should fix it, I think. And if we run that, now we won't get a legend because it's not seeing those as aesthetic mappings. I guess I need to make that green. They're just mapping to a constant. Okay, so there are some issues that are common when you're generating graphs, and one of the issues is this concept of overplotting. So the idea is that there's just too many points or too many records to actually show effectively individually. So to replicate that issue here, I'm creating 15,000 random coordinates and then 15,000 additional random coordinates, and this is using the R norm. So it's basically it's picking values from a normal distribution with a mean of 0 and a standard deviation of 1. Then I merge those into a data frame, and then I plot one of them to the x-axis and one to the y-axis. So if I plot that, and sometimes this takes a second, you see there's tons of points. So that there's 15,000 points represented in that space. So we might want to be able to try to maybe generalize it a bit and deal with this overplotting issue. So there are multiple ways to do it. One way to do it is through binning. So this is hexagon binning, and the idea is that you're replacing each individual point with a count of features within an area defined by hexagon. So now, instead of using geom point here, we've replaced it with geom hex, and we've set a size argument. So let's run that, You can see now we plot out hexagons, and it's clear to see that the bulk of the density is kind of in the middle, and that's not as obvious here. And that should make sense with this data because it's a random normal distribution, so it's more likely to sample things closer to the mean than further away from the mean, right? And by the way, if you're running this, you'll get slightly different result because these are like, randomly generated up here in this code. Again, if we change the size of this, let me just drop it down to like 1, then you get different size bins. That's probably too big. Seem to be changing it much. Okay, so that's a hex bin. Now, another way you can do it is what's known as Geom bin 2D, and effectively that basically makes rectangular bins. So there you go. So instead of it being a hexagon, it's a rectangle, and you can give it different shapes and different dimensions. This is just 1 by 1, but you could also, if you wanted to have more detail, we could do like a 0.2 by 0.2 and see what that looks like. And then obviously bigger would make you have a bigger, larger bins. And also too, they don't have to be the same size. So you could do something like 0.5 by 1. So they're not they're rectangular now instead of square. So that's a 2D bin. Another option is Geom Density 2D, and effectively this is a kernel density, but now it's being interpolated over 2-dimensional space instead of 1-dimensional space. If you're a GIS person, you may be familiar with like kernel density grids. This is basically the same thing. So again, we're just swapping this out here. And we get back this. And note this has 2 components. We have we basically have a grid surface, like a cell or grid surface, and then I added a second. Stat density is what gives you the surface, and then the second one here is I basically added contour lines to it. Okay. Geom jitter is used to add some random noise to points. Sometimes this can be useful if things overlap a bit, or you have like groupings and you want to just have it jittered around the group. So basically Geom jitter just adds in, this is the original graph, so let's start with this. So basically I just created this data, which is just 1 matched with 1 through 5, 2 matched with 1 through 5. So we get this kind of pattern that's just very, it's basically a regular grid. What Geom jitter does is this adds a little bit of noise to that, so they're not quite as, stacked. So that can help a little bit with like overplotting too. Okay, and then this last section is not super important for us, but I did just want to note that all this is basically just built on top of simple geometric primitives. So you can actually specify like the dimensions of a polygon or of a rectangle, of like line segments, and basically you can build all those things up to generate graphs. So here I have a polygon where I defined the XY coordinates of its like vertices, and a rectangular box, and then a line geometry. So these kind of simple primitives are really what is going on behind the scenes in ggplot when you create a line or a point or a box plot or whatever. Okay, and then just as kind of a final note, all the graphs we looked at here were inside of like a regular Cartesian coordinate space, but you can also use different coordinate spaces. So here I'm just showing an example of using polar coordinates as opposed to the Cartesian coordinates. Now, if I comment it out, actually, let me comment this out. Now, if I run that, this is what it would look like. Did it not run? Oh, I saved this to a variable, so I have to call the variable. That's right. So let me do. There we go. So that'll plot it. So here I'm saving the graph to a variable, so it didn't plot. So you have to call the variable in order to actually get it to plot. So this is the original geometry. And then if I get rid of this and set this back up, this chord polar transforms it into polar coordinates as opposed to the Cartesian coordinates. So you get something like that. Okay, so again, if you want to learn more about ggplot, there are some books on the topic. There's a lot of good help online. Again, the cheat sheet is really good, so I definitely would recommend having a look at that. There are other geometries that we didn't talk about that are worth investigating and looking at. In the next video, I'm just going to go through some examples of how to clean up your graphs a bit. So that'll be the next set of the next video.